JEP 442, Foreign Function and Memory API, third preview. Summary. Introduce an API by which Java programs can interoperate with code and data outside of the Java runtime. By efficiently invoking foreign functions, i.e., code outside the JVM, and by safely accessing foreign memory, i.e., memory not managed by the JVM, the API enables Java programs to call native libraries and process native data without the brittleness and danger of JNI. This is a preview API. History. The Foreign Function and Memory (FFM) API first previewed in JDK 19 via JEP 424, then previewed again in JDK 20 via JEP 434. This JEP proposes a third preview to incorporate refinements based on feedback. In this version we have 1. Centralized the management of the lifetimes of native segments in the Arena interface. 2. Enhanced layout paths with a new element to dereference address layouts. 3. Provided a linker option to optimize calls to functions that are short-lived and will not upcall to Java, for example, clock_getTime. 4. Provided a fallback native linker implementation, based on libv, to facilitate porting, and 5. Removed the var list class. Goals. 1. Ease of use. Replace the Java Native Interface, JNI, with a superior, pure Java development model. 2. Performance. Provide performance that is comparable to, if not better than, existing APIs such as JNI and sun.miscellaneous.unsafe. 3. Generality. Provide ways to operate on different kinds of foreign memory, for example, native memory, persistent memory, and managed heap memory, and, over time, to accommodate other platforms, for example, 32-bit x86, and foreign functions written in languages other than C, for example, C++, Fortran. 4. Safety. Allow programs to perform unsafe operations on foreign memory, but warn users about such operations by default. Non-goals. It is not a goal to 1. Re-implement JNI on top of this API, or otherwise change JNI in any way. 2. Re-implement legacy Java APIs, such as sun.miscellaneous.unsafe, on top of this API. 3. Provide tooling that mechanically generates Java code from native code header files, or 4. Change how Java applications that interact with native libraries are packaged and deployed, for example, via multi-platform jar files. Motivation. The Java platform has always offered a rich foundation to library and application developers who wish to reach beyond the JVM and interact with other platforms. Java APIs expose non-Java resources conveniently and reliably, whether to access remote data, JDBC, invoke web services, HTTP client, serve remote clients, NIO channels, or communicate with local processes, Unix domain sockets. Unfortunately, Java developers still face significant obstacles in accessing an important kind of non-Java resource, code and data on the same machine as the JVM, but outside the Java runtime. Foreign memory. Objects created with the new keyword are stored in the JVM's heap, where they are subject to garbage collection when no longer needed. However, the cost and unpredictability of garbage collection is unacceptable for performance-critical libraries such as TensorFlow, Ignite, Lucene, and Netty. They need to store data outside the heap, in off-heap memory which they allocate and deallocate themselves. Access to off-heap memory also allows data to be serialized and deserialized by mapping files directly into memory via, for example, map. The Java platform has historically provided two APIs for accessing off-heap memory. 1. The Byte Buffer API provides direct byte buffers, which are Java objects backed by fixed-size regions of off-heap memory. However, the maximum size of a region is limited to 2 GB and the methods for reading and writing memory are rudimentary and error-prone, providing little more than indexed access to primitive values. More seriously, the memory which backs a direct byte buffer is deallocated only when the buffer object is garbage collected, which the developer cannot control. The lack of support for timely deallocation makes the byte buffer API a bad fit for systems programming in Java. 2. The sun.miscellaneous.unsafe API provides low-level access to on-heap memory that also works for off-heap memory. Using unsafe is fast, because its memory access operations are intrinsified by the JVM, allows huge off-heap regions, theoretically up to 16 exabytes, and offers fine-grained control over deallocation, because unsafe free memory can be called at any time. However, this programming model is weak because it gives the developer too much control. A library in a long-running server application will allocate and interact with multiple regions of off-heap memory over time. Data in one region will point to data in another region, and regions must be deallocated in the correct order or else dangling pointers will cause use after free bugs. The lack of support for safe deallocation makes the unsafe API a bad fit for systems programming in Java. The same criticism applies to APIs outside the JDK that offer fine-grained allocation and deallocation by wrapping native code, which calls malloc and free. In summary, sophisticated clients deserve an API that can allocate, manipulate, and share off-heap memory with the same fluidity and safety as on-heap memory. Such an API should balance the need for predictable deallocation with the need to prevent untimely deallocation that can lead to JVM crashes or, worse, to silent memory corruption. Foreign functions. JNI has supported the invocation of native code, i.e., foreign functions, since Java 1.1, but it is inadequate for many reasons. 1. JNI involves several tedious artifacts: a Java API, native methods, a C header file derived from the Java API, and a C implementation that calls the native library of interest. Java developers must work across multiple toolchains to keep platform-dependent artifacts in sync, which is especially burdensome when the native library evolves rapidly. 2. JNI can only interoperate with libraries written in languages, typically C and C++, that use the calling convention of the operating system and CPU for which the JVM was built. A native method cannot be used to invoke a function written in a language that uses a different convention. 3. JNI does not reconcile the Java type system with the C type system. Aggregate data in Java is represented with objects, but aggregate data in C is represented with structs, so any Java object passed to a native method must be laboriously unpacked by native code. For example, consider a record class person in Java. Passing a person object to a native method will require the native code to use JNI C API to extract fields, for example, first name and last name, from the object. As a result, Java developers sometimes flatten their data into a single object, for example, a byte array or a direct byte buffer, but more often, since passing Java objects via JNI is slow, they use the unsafe API to allocate off-heap memory and pass its address to a native method as a long, which makes the Java code tragically unsafe. Over the years, numerous frameworks have emerged to fill the gaps left by JNI, including JNA, Junior and Java CPP. These frameworks are often a marked improvement over JNI, but the situation is still less than ideal, especially when compared with languages which offer first-class native interoperation. For example, Python's types package can dynamically wrap functions in native libraries without any glue code. Other languages, such as Rust, provide tools which mechanically derive native wrappers from C++ header files. Ultimately, Java developers should have a supported API that lets them straightforwardly consume any native library deemed useful for a particular task, without the tedious glue and clunkiness of JNI. An excellent abstraction to build upon is method handles, introduced in Java 7 to support fast dynamic languages on the JVM. Exposing native code via method handles would radically simplify the task of writing, building, and distributing Java libraries which depend upon native libraries. Furthermore, an API capable of modeling foreign functions, i.e., native code, and foreign memory, i.e., off-heap data, would provide a solid foundation for third-party native interoperation frameworks. Description: the Foreign Function and Memory API, FFM API, defines classes and interfaces so that client code in libraries and applications can 1. Control the allocation and deallocation of foreign memory. Memory segment, arena, and segment allocator. 2. Manipulate and access structured foreign memory. Memory layout and var handle, and 3. Call foreign functions, linker, function descriptor, and symbol lookup. The FFM API resides in the java.lang.foreign package of the java.base module. Example. As a brief example of using the FFM API, here is Java code that obtains a method handle for a C library function radix sort and then uses it to sort 4 strings which start life in a Java array. A few details are elided. Because the FFM API is a preview API, you must compile and run the code with preview features enabled, i.e., Javac Release 21 Enable Preview, and Java Enable Preview. //1. Find foreign function on the C library path. Linker equals linker.native linker, symbol lookup stlib equals linker.default lookup, method handle radix sort equals linker.downcall handle stlib.find radix sort, //2. Allocate on heap memory to store 4 strings. String, Java strings equals, mouse, cat, dog, car, //3. Use try with resources to manage the lifetime of off-heap memory. Try, arena off-heap equals arena.of_confined, //4. Allocate a region of off-heap memory to store 4 pointers. Memory segment pointers equals off-heap.allocate array value layout.address, java strings.length, //5. Copy the strings from on-heap to off-heap.
4. Int I equals 0, I less than java strings.length, I++. Memory segment C string equals off-heap.allocate utfate string java strings I, pointers.set at index value layout.address, I, C, string.
//6. Sort the off-heap data by calling the foreign function. Radix sort.invoke pointers, java strings.length, memory segment.null, \0, //7. Copy the, reordered, strings from off-heap to on-heap. 4. Int I equals 0, I less than java strings.length, I++. Memory segment C string equals pointers.get at index value layout.address, I, java strings I, equals C string.get utf8 string 0. //8. All off-heap memory is deallocated here. Assert arrays. Equals java strings, new string, car, cat, dog, mouse, //true. This code is far clearer than any solution that uses JNI, since implicit conversions and memory access that would have been hidden behind native method calls are now expressed directly in Java. Modern Java idioms can also be used. For example, streams can allow multiple threads to copy data between on-heap and off-heap memory in parallel. Memory segments and arenas. A memory segment is an abstraction backed by a contiguous region of memory, located either off-heap or on-heap. A memory segment can be 1. A native segment, allocated from scratch in off-heap memory, as if via malloc. 2. A mapped segment, wrapped around a region of mapped off-heap memory, as if via map, or 3. An array or buffer segment, wrapped around a region of on-heap memory associated with an existing Java array or byte buffer, respectively. All memory segments provide spatial and temporal bounds which ensure that memory access operations are safe. In a nutshell, the bounds guarantee no use of unallocated memory and no use after free. The spatial bounds of a segment determine the range of memory addresses associated with the segment. For example, the code below allocates a native segment of 100 bytes, so the associated range of addresses is from some base address B to B plus 99 inclusive. Memory segment data equals arena.global. Allocate 100. The temporal bounds of a segment determine its lifetime, that is, the period until the region of memory which backs the segment is deallocated. The FFM API guarantees that a memory segment cannot be accessed after its backing region of memory is deallocated. The temporal bounds of a segment are determined by the arena used to allocate the segment. Multiple segments allocated in the same arena have the same temporal bounds, and can safely contain mutual references. Segment A can hold a pointer to an address in segment B, and segment B can hold a pointer to an address in segment A, and both segments will be deallocated at the same time so that neither segment has a dangling pointer. The simplest arena is the global arena, which provides an unbounded lifetime. It is always alive. A segment allocated in the global arena, as in the code above, is always accessible, and the region of memory backing the segment is never deallocated. Most programs, though, require off-heap memory to be deallocated while the program is running, and thus need memory segments with bounded lifetimes. An automatic arena provides a bounded lifetime. A segment allocated by an automatic arena can be accessed until the JVM's garbage collector detects that the memory segment is unreachable, at which point the region of memory backing the segment is deallocated. For example, this method allocates a segment in an automatic arena. Void process data, memory segment data equals arena.of_auto. Allocate native 100, use the data variable some more, / the region of memory backing the data segment. / is deallocated here, or later. As long as the data variable does not leak out of the method, the segment will eventually be detected as unreachable and its backing region will be deallocated. An automatic arena's bounded but non-deterministic lifetime is not always sufficient. For example, an API that maps a memory segment from a file should allow the client to deterministically deallocate the region of memory backing the segment, since waiting for the garbage collector to do so could adversely affect performance. A confined arena provides a bounded and deterministic lifetime. It is alive from the time the client opens the arena until the time the client closes the arena. A memory segment allocated in a confined arena can be accessed only before the arena is closed, at which point the region of memory backing the segment is deallocated. Attempts to access a memory segment after its arena is closed will fail, with an exception. For example, this code opens an arena and uses the arena to allocate two segments. Memory segment input equals null, output equals null, try, arena processing equals arena.of_confined. Input equals processing.allocate 100, set up data in input, output equals processing.allocate 100, process data from input to output, calculate the ultimate result from output and store it elsewhere. / the regions of memory backing the segments are deallocated here, input.getValueLayout.java_byte, 0, / throws illegal state exception. / also for output, exiting the try with resources block closes the arena, at which point all segments allocated by the arena are invalidated atomically and the regions of memory backing the segments are deallocated. A confined arena's deterministic lifetime comes at a price. Only one thread can access the memory segments allocated in a confined arena. If multiple threads need access to a segment, then a shared arena can be used. The memory segments allocated in a shared arena can be accessed by multiple threads, and any thread, whether it accesses the region or not, can close the arena to deallocate the segments. Closing the arena atomically invalidates the segments, though the deallocation of the regions of memory backing the segments might not occur immediately, since an expensive synchronization operation is needed to detect and cancel pending concurrent access operations on the segments. In summary, an arena controls which threads can access a memory segment, and when, in order to provide both strong temporal safety and a predictable performance model. The FFM API offers a choice of arenas so that a client can trade off breadth of access against timeliness of deallocation. Dereferencing segments. To dereference some data in a memory segment, we need to take into account several factors. 1. The number of bytes to be dereferenced. 2. The alignment constraints of the address at which dereference occurs. 3. The endianness with which bytes are stored in the memory segment, and 4. The Java type to be used in the dereference operation, for example, int versus float. All these characteristics are captured in the value layout abstraction. For example, the predefined Java_int value layout is 4 bytes wide, is aligned on 4-byte boundaries, uses the native platform endianness, for example, little endian on Linux/x64, and is associated with the Java type int. Memory segments have simple dereference methods to read and write values from and to memory segments. These methods accept a value layout, which uniquely specifies the properties of the dereference operation. For example, we can write 25 int values at consecutive offsets in a memory segment. Memory segment equals arena.of_auto. Allocate 100//size. Value layout.java_int. Byte alignment //alignment. 4. Int I equals 0, I less than 25, I++. Segment.setAtIndex value layout.java_int index, I, value to write, I. Memory layouts and structured access. Consider the following C declaration, which defines an array of point structs, where each point struct has two members, namely point.x and point.y. Struct point, int x, int y, PTS 10. Using the dereference methods shown in the previous section, to initialize such a native array we would have to write the following code. We assume that size of int equals 4. Memory segment equals arena.of_auto. Allocate to value layout.java_int. Byte size 10, //size. Value layout.java_int. Byte alignment, //alignment. 4. Int I equals 0, I less than 10, I++. Segment.setAtIndex value layout.java_int index, I2. Value to write, I, //x. Segment.setAtIndex value layout.java_int index, I2, +1. Value to write, I, //y. To reduce the need for tedious calculations about memory layout, for example, I2, +1 in the example above, a memory layout can be used to describe the content of a memory segment in a more declarative fashion. For example, the desired layout of the native memory segment in the examples above can be described via sequence layout PTS layout equals memory layout.sequence layout 10, memory layout.struct layout value layout.java_int. With name x, value layout.java_int. With name y. This creates a sequence memory layout containing 10 repetitions of a struct layout whose elements are two Java_int layouts named x and y, respectively. Given this layout, we can avoid calculating offsets in our code by creating two memory access var handles, special var handles which accept a memory segment parameter, the segment to be dereferenced, followed by one or more long coordinates, the indices at which the dereference operation should occur. Var handle x handle // memory segment long greater than int equals pts layout.var handle path element.sequence element path element.group element x var handle e handle // memory segment long greater than int equals pts layout.var handle path element.sequence element path element.group element y. Memory segment equals arena.of_auto. Allocate PTS layout, 4, int I equals 0, I less than PTS layout.element count, I++, x handle.set segment, index, long, I, value to write, I, //x, y handle.set segment, index, long, I, value to write, I, //y. The PTS layout object drives the creation of the memory access var handle through the creation of a layout path, which is used to select a nested layout from a complex layout expression. Since the selected value layout is associated with the Java type int, the type of the resulting var handles x handle and y handle will also be int. Moreover, since the selected value layout is defined inside a sequence layout, the var handles acquire an extra coordinate of type long, namely the index of the point struct whose coordinate is to be read or written. The PTS layout object also drives the allocation of the native memory segment, which is based upon size and alignment information derived from the layout. Offset computations are no longer needed inside the loop since distinct var handles are used to initialize the point.x and point.y elements. Segment allocators. Memory allocation is often a bottleneck when clients use off-heap memory. The FFM API therefore includes a segment allocator abstraction to define operations to allocate and initialize memory segments. As a convenience, the Arena class implements the segment allocator interface so that arenas can be used to allocate native segments. In other words, Arena is a one-stop shop for flexible allocation and timely deallocation of off-heap memory. Try Arena off-heap equals arena.of-confined. Memory segment native array equals off-heap.allocate array value layout.java_int 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Memory segment native string equals off-heap.allocate ut8 string hello. Memory segment upcall stub equals linker.upcall stub handle DSC off-heap / memory released here. Segment allocators can also be obtained via factories in the segment allocator interface. For example, one factory creates a slicing allocator that responds to allocation requests by returning memory segments which are part of a previously allocated segment. Thus, many requests can be satisfied without physically allocating more memory. The following code obtains a slicing allocator over an existing segment and then uses it to allocate a segment initialized from a Java array. Memory segment equals segment allocator equals segment allocator dot slicing allocator segment 4 int I equals 0 I less than 10 I plus plus. Memory segment s equals allocator dot allocate array java underscore int 1 2 3 4 5. Segment allocators can be used as building blocks to create arenas that support custom allocation strategies. For example, if a large number of native segments will share the same bounded lifetime, then a custom arena could use a slicing allocator to allocate the segments efficiently. This lets clients enjoy both scalable allocation, thanks to slicing, and deterministic deallocation, thanks to the arena. As an example, the following code defines a slicing arena that behaves like a confined arena but internally uses a slicing allocator to respond to allocation requests. When the slicing arena is closed, the underlying confined arena is closed, invalidating all segments allocated in the slicing arena. Some details are elided. Class slicing arena implements arena, final arena equals arena.of-confined, final segment allocator slicing, allocator. Slicing arena long size. Slicing allocator equals segment allocator dot slicing allocator arena.allocate size. Public void allocate long byte size, long byte alignment. Return slicing allocator dot allocate byte size, byte alignment. Public void close, return arena dot close. The earlier code which used a slicing allocator directly can now be written more succinctly. Try arena slicing arena equals new slicing arena 1000. 4 int I equals 0 I less than 10 I plus plus. Memory segment s equals slicing arena dot allocate array java underscore int 1 2 3 4 5 / all memory allocated is released here. Looking up foreign functions. The first ingredient of any support for foreign functions is a mechanism to find the address of a given symbol in a loaded native library. This capability, represented by a symbol lookup object, is crucial for linking Java code to foreign functions, see below. The FFM API supports 3 different kinds of symbol lookup objects. 1. Symbol lookup : library lookup string, arena, creates a library lookup, which locates all the symbols in a user-specified native library. Creating the lookup object causes the library to be loaded, for example, using glopen, and associated with the arena object. The library is unloaded, for example, using close, when the provided arena is closed. 2. Symbol lookup : loader lookup creates a loader lookup, which locates all the symbols in all the native libraries that have been loaded by classes in the current class loader using the system::load library and system::load methods. 3. Linker::default lookup creates a default lookup, which locates all the symbols in libraries that are commonly used on the OS and processor combination associated with the linker instance. Given a symbol lookup, a client can find a foreign function with the symbol lookup::findString method. If the named function is present among the symbols seen by the symbol lookup, then the method returns a zero-length memory segment, see below, whose base address points to the function's entry point. For example, the following code uses a loader lookup to load the OpenGL library and find the address of its GL getString function. Try arena equals arena.of_confined. Symbol lookup OpenGL equals symbol lookup.library lookup libl.so, arena, memory segment GL version equals OpenGL.find GL getString. Get //libl.so unloaded here. Symbol lookup::library lookup string, arena, differs from JNI's library loading mechanism, i.e., system::load library, in an important way. Native libraries designed to work with JNI can use JNI functions to perform Java operations, such as object allocation or method access, which might trigger class loading. Therefore, such JNI-affiliated libraries must be associated with a class loader when they are loaded by the JVM. Then, to preserve class loader integrity, the same JNI-affiliated library cannot be loaded from classes defined in different class loaders. In contrast, the FFM API does not offer functions for native code to access the Java environment, and does not assume that native libraries are designed to work with the FFM API. The native libraries loaded via symbol lookup::library lookup string, arena, are unaware that they are accessed from code running in a JVM, and make no attempt to perform Java operations. As such, they are not tied to a particular class loader and can be reloaded as many times as needed by FFM API clients in different loaders. Linking Java code to foreign functions. The linker interface is the core of how Java code interoperates with foreign code. While in this document we often refer to interoperation between Java and C libraries, the concepts in this interface are general enough to support other non-Java languages in future. The linker interface enables both down calls from Java code to native code, and up calls from native code back to Java code. Interface linker, method handle down call handle memory segment address, function descriptor function, memory segment up call stub method handle target, function descriptor function, arena. For down calls, the down call handle method takes the address of a foreign function, typically a memory segment obtained from a library lookup, and exposes the foreign function as a down call method handle. Later, Java code invokes the down call method handle by calling its invoke, or invokeExact, method, and the foreign function runs. Any arguments passed to the method handle's invoke method are passed on to the foreign function. For up calls, the up call stub method takes a method handle, typically one which refers to a Java method, rather than a down call method handle, and converts it to a memory segment instance. Later, the memory segment is passed as an argument when Java code invokes a down call method handle. In effect, the memory segment serves as a function pointer. For more information on up calls, see below. Suppose we wish to down call from Java to the strlen function defined in the standard C library. size_t strlen const char s. Clients can link C functions using the native linker, clinker::native linker, a linker implementation that conforms to the ABI determined by the OS and CPU on which the JVM is running. A downcall method handle that exposes strlen can be obtained as follows. The details of function descriptor will be described shortly. Linker equals linker.native linker, method handle strlen equals linker.downcall handle linker.default lookup. Find strlen. Get function descriptor of Java_long address. Invoking the downcall method handle will run strlen and make its result available in Java. For the argument to strlen we use a helper method to convert a Java string into an off-heap memory segment, using a confined arena, which is then passed by reference. Try arena equals arena.of confined. Memory segment str equals arena.allocate 8 string hello, long len equals, long, strlen.invoke str, //5. Method handles work well for exposing foreign functions because the JVM already optimizes the invocation of method handles all the way down to native code. When a method handle refers to a method in a class file, invoking the method handle typically causes the target method to be JIT compiled. Subsequently, the JVM interprets the Java bytecode that calls method handle invoke exact by transferring control to the assembly code generated for the target method. Thus, a traditional method handle in Java targets non-Java code behind the scenes. A downcall method handle is a natural extension that lets developers target non-Java code explicitly. Method handles also enjoy a property called signature polymorphism, which allows box-free invocation with primitive arguments. In sum, method handles let the linker expose foreign functions in a natural, efficient, and extensible manner. Describing C types in Java. To create a downcall method handle, the FFM API requires the client to provide a function descriptor that describes the C parameter types and C return type of the target C function. C types are described in the FFM API by memory layout objects such as value layout for scalar C types and group layout for C struct types. Clients usually have memory layout objects on hand to dereference data in foreign memory, and can reuse them to obtain a function descriptor. The FFM API also uses the function descriptor to derive the type of the downcall method handle. Every method handle is strongly typed, which means it is stringent about the number and types of the arguments that can be passed to its invoke exact method at runtime. For example, a method handle created to take one memory segment argument cannot be invoked via invoke exact memory segment, even though invoke exact is a vargs method. The type of the downcall method handles ascribes the Java signature which clients must use when invoking the downcall method handle. It is, effectively, the Java view of the C function. As an example, suppose a downcall method handle should expose a C function that takes a C int and returns a C long. On Linux/x64 and Mac OS x64, the C types long and int are associated with the predefined layouts Java_long and Java_int respectively, so the required function descriptor can be obtained with function descriptor of Java_long, Java_int. The native linker will then arrange for the type of the downcall method handle to be the Java signature int to long. Clients must be aware of the current platform if they target C functions which use scalar types such as long, int, and size_t. This is because the association of scalar C types with layout constants varies by platform. On Windows/x64, a C long is associated with the Java_int layout, so the required function descriptor would be function descriptor of Java_int, Java_int, and the type of the downcall method handle would be the Java signature int to int. As another example, suppose a downcall method handle should expose a void C function that takes a pointer. On all platforms, a C pointer type is associated with the predefined layout address, so the required function descriptor can be obtained with function descriptor of void address. The native linker will then arrange for the type of the downcall method handle to be the Java signature memory segment to void. That is, a memory segment parameter can be passed by reference, or by value, depending on the layout specified in the corresponding function descriptor. Clients can use C pointers without being aware of the current platform. Clients do not need to know the size of pointers on the current platform, since the size of the address layout is inferred from the current platform, nor do clients need to distinguish between C pointer types such as int and char. Finally, unlike JNI, the native linker supports passing structured data to foreign functions. Suppose a downcall method handle should expose a void C function that takes a struct, described by this layout. Memory layout system time equals memory layout.of struct Java_short. With name W year, Java_short. With name W month, Java_short. With name W day of week, Java underscore short dot with name wday, Java underscore short dot with name whour, Java underscore short dot with name wminute, Java underscore short dot with name wsecond, Java underscore short dot with name milliseconds. The required function descriptor can be obtained with function descriptor avoid system time. The linker will arrange for the type of the downcall method handle to be the Java signature memory segment void. The memory layout associated with a C struct type must be a composite layout which defines the sub-layouts for all the fields in the C struct, including any platform-dependent padding a native compiler might insert. If a C function returns a by value struct, not shown here, then a fresh memory segment must be allocated off heap and returned to the Java client. To achieve this, the method handle returned by downcall handle requires an additional segment allocator argument which the FFM API uses to allocate a memory segment to hold the struct returned by the C function. As mentioned earlier, while the native linker implementation is focused on providing interoperation between Java and C libraries, the linker interface is language neutral. It has no specific knowledge of how C types are defined, so clients are responsible for obtaining suitable layout definitions for C types. This choice is deliberate, since layout definitions for C types, whether simple scalars or complex structs, are ultimately platform dependent, and can therefore be mechanically generated by a tool that has an intimate understanding of the given target platform. Packaging Java arguments for C functions. A calling convention enables interoperation between different languages by specifying how code in one language invokes a function in another language, passes arguments, and receives results. The linker API is neutral with respect to calling conventions, but the native linker implementation supports several calling conventions out of the box: Linux/x64, Linux/Arch64, Linux/RISC-V, macOS x64, macOS Arch64, Windows/x64 and Windows/Arch64. Additional platforms are supported via the fallback linker, which is a native linker implementation based on libv. Being written in Java, the linker API is far easier to maintain and extend than JNI, whose calling conventions are hardwired into hotspot C++ code. Consider the function descriptor obtained above for the system time struct/layout. Given the calling convention of the OS and CPU where the JVM is running, the native linker uses the function descriptor to infer how the struct's fields should be passed to the C function when a downcall method handle is invoked with a memory segment argument. For one calling convention, the native linker implementation could arrange to decompose the incoming memory segment, pass the first 4 fields using general CPU registers, and pass the remaining fields on the C stack. For a different calling convention, the native linker implementation could arrange to pass the struct indirectly by allocating a region of memory, bulk copying the contents of the incoming memory segment into that region, and passing a pointer to that region to the C function. This lowest level packaging of arguments happens behind the scenes, without any need for supervision by client code. Zero-length memory segments. Foreign functions often allocate a region of memory and return a pointer to that region. Modeling such a region with a memory segment is challenging because the region's size is not available to the Java runtime. For example, a C function with return type char might return a pointer to a region containing a single char value or to a region containing a sequence of char values terminated by \0. The size of the region is not readily apparent to the code calling the foreign function. The FFM API represents a pointer returned from a foreign function as a zero-length memory segment. The address of the segment is the value of the pointer, and the size of the segment is 0. Similarly, when a client reads a pointer from a memory segment, then a zero-length memory segment is returned. A zero-length segment has trivial spatial bounds, so any attempt to access such a segment fails with index out-of-bounds exception. This is a crucial safety feature, since these segments are associated with a region of memory whose size is not known. Access operations involving these segments cannot be validated. In effect, a zero-length memory segment wraps an address, and it cannot be used without explicit intent. Clients can turn a zero-length memory segment into a native segment of their chosen size via the method memory segment:\reinterpret. This method attaches fresh spatial and temporal bounds to a zero-length memory segment in order to allow dereference operations. The memory segment returned by this method is unsafe. A zero-length memory segment might be backed by a region of memory that is 10 bytes long, but the client might overestimate the size of the region and use memory segment reinterpret to obtain a segment that is 100 bytes long. Later, this might result in attempts to dereference memory outside the bounds of the region, which might cause a JVM crash or, even worse, result in silent memory corruption. Overriding the spatial and temporal bounds of a zero-length memory segment is unsafe. For this reason, the memory segment reinterpret method is restricted, and using it in a program causes the Java runtime to issue warnings. See more below. Upcalls. Sometimes it is useful to pass Java code as a function pointer to some foreign function. We can do that by using the linker support for upcalls. In this section we build, piece by piece, a more sophisticated example which demonstrates the full power of the linker, with full bidirectional interoperation of both code and data across the Java/native boundary. Consider this function defined in the standard C library. Void sort void base, size _t num, size _t size, int, compare const void. To call sort from Java, we first need to create a downcall method handle. Linker equals linker.native linker, method handle sort equals linker.downcall handle linker.default lookup. Find sort. Get, function descriptor.avoid address, Java_long, address. As before, we use the Java_long layout to map the C size _t type, and we use the address layout for both the first pointer parameter, the array pointer, and the last parameter, the function pointer. Sort sorts the contents of an array using a custom comparator function, compare, passed as a function pointer. Therefore, to invoke the downcall method handle we need a function pointer to pass as the last parameter to the method handle's invoke exact method. Linker::upcall stub helps us create function pointers by using existing method handles, as follows. First, we write a static method in Java that compares two int values, represented indirectly as memory segment objects. Class sort, static int sort compare memory segment elem1, memory segment elem2. Return integer.compare elem1.get java_int, 0. elem2.get java_int, 0. Second, we create a method handle pointing to the Java comparator method. Method handle compare handle equals method handles.lookup find static sort.class, sort compare, method type int.class, memory segment.class, memory segment.class. Third, now that we have a method handle for our Java comparator, we can create a function pointer using linker::upcall stub. Just as for downcalls, we describe the signature of the function pointer using a function descriptor. Memory segment compare func equals linker.upcall stub compare handle, a Java description of a C function implemented by a Java method. Function descriptor.of Java_int, address. With target layout Java_int, address. With target layout Java_int, arena.of auto. We finally have a memory segment, compare func, which points to a stub that can be used to invoke our Java comparator function, and so we now have all we need to invoke the sort downcall handle. Try arena equals arena.of confined memory segment array equals arena.allocate array value layout.java_int, 0, 9, 3, 4, 6, 5, 1, 8, 2, 7, sort.invoke array, 10 liters, value layout.java_int. Byte size, compare func, int, sorted equals array.toInt array, / 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This code creates an off-heap array, copies the contents of a Java array into it, and then passes the array to the sort handle along with the comparator function we obtained from the native linker. After the invocation, the contents of the off-heap array will be sorted according to our comparator function, written in Java. We then extract a new Java array from the segment, which contains the sorted elements. Safety. Fundamentally, any interaction between Java code and native code can compromise the integrity of the Java platform. Linking to a C function in a precompiled library is inherently unreliable because the Java runtime cannot guarantee that the function's signature matches the expectations of the Java code, or even that a symbol in a C library is really a function. Moreover, even if a suitable function is linked, actually calling the function can lead to low-level failures, such as segmentation faults, that end up crashing the VM. Such failures cannot be prevented by the Java runtime or caught by Java code. Native code that uses JNI functions is especially dangerous. Such code can access JDK internals without command line flags, for example, add opens, by using functions such as getStaticField and callVirtual method. It can also change the values of final fields long after they are initialized. Allowing native code to bypass the checks applied to Java code undermines every boundary and assumption in the JDK. In other words, JNI is inherently unsafe. JNI cannot be disabled, so there is no way to ensure that Java code will not call native code which uses dangerous JNI functions. This is a risk to platform integrity that is almost invisible to application developers and end users because 99% of the use of these functions is typically from third, fourth, and fifth-party libraries sandwiched between the application and the JDK. Most of the FFM API is safe by design. Many scenarios that required the use of JNI and native code in the past can be accomplished by calling methods in the FFM API, which cannot compromise the Java platform. For example, a primary use case for JNI, flexible memory allocation, is supported with a simple method, memory segment :allocate native, that involves no native code and always returns memory managed by the Java runtime. Generally speaking, Java code that uses the FFM API cannot crash the JVM. Part of the FFM API, however, is inherently unsafe. When interacting with the linker, Java code can request a downcall method handle by specifying parameter types that are incompatible with those of the underlying foreign function. Invoking the downcall method handle in Java will result in the same kind of outcome, a VM crash, or undefined behavior, that can occur when invoking a native method in JNI. The FFM API can also produce unsafe segments, that is, memory segments whose spatial and temporal bounds are user-provided and cannot be verified by the Java runtime. See memory segment :reinterpret. The unsafe methods in the FFM API do not pose the same risks as JNI functions. They cannot, for example, change the values of final fields in Java objects. On the other hand, the unsafe methods in the FFM API are easy to call from Java code. For this reason, the use of unsafe methods in the FFM API is restricted. Their use is permitted but, by default, every such use causes a warning to be issued at runtime. To allow code in a module M to use unsafe methods without warnings, specify the Enable Native Access =M option on the Java command line. Specify multiple modules with a comma-separated list. Specify all unnamed to enable warning-free use for all code on the class path. When this option is present, any use of unsafe methods from outside the list of specified modules will cause an illegal caller exception to be thrown, rather than a warning to be issued. In a future release, it is likely that this option will be required in order to use unsafe methods. We do not propose here to restrict any aspect of JNI. It will still be possible to call native methods in Java, and for native code to call unsafe JNI functions. However, it is likely that we will restrict JNI in some way in a future release. For example, unsafe JNI functions such as new direct byte buffer may be disabled by default, just like unsafe methods in the FFM API. More broadly, the JNI mechanism is so irredeemably dangerous that we hope libraries will prefer the pure Java FFM API for both safe and unsafe operations so that, in time, we can disable all of JNI by default. This aligns with the broader Java roadmap of making the platform safe out of the box, requiring end users to opt into unsafe activities such as breaking strong encapsulation or linking to unknown code. We do not propose here to change sun.miscellaneous.unsafe in any way. The FFM API's support for off-heap memory is an excellent alternative to the wrappers around malloc and free in sun.miscellaneous.unsafe, namely allocate memory, set memory, copy memory, and free memory. We hope that libraries and applications that require off-heap storage adopt the FFM API so that, in time, we can deprecate and then eventually remove these sun.miscellaneous.unsafe methods. Alternatives: keep using java.nio.bytebuffer, sun.miscellaneous.unsafe, JNI, and other third-party frameworks. Risks and assumptions. Creating an API to access foreign memory in a way that is both safe and efficient is a daunting task. Since the spatial and temporal checks described in the previous sections need to be performed upon every access, it is crucial that JEP compilers be able to optimize away these checks by, for example, hoisting them outside of hot loops. The JET implementations will likely require some work to ensure that uses of the API are as efficient and optimizable as uses of existing APIs such as bytebuffer and unsafe. The JET implementations will also require work to ensure that uses of the native method handles retrieved from the API are at least as efficient and optimizable as uses of existing JNI native methods. Dependencies. 1. The foreign function and memory API can be used to access non-volatile memory, already possible via JEP 352, non-volatile mapped byte buffers, in a more general and efficient way. 2. The work described here will likely enable subsequent work to provide a tool, JEXtract, which, starting from the header files for a given native library, mechanically generates the native method handles required to interoperate with that library. This will further reduce the overhead of using native libraries from Java.